Hello everyone. As Steve said, my name is Matthew Weier. I work with JKTech and am very heavily involved in the JK drop weight and SMC tests. My background is in analytical test methods, and I'm drawing on that to discuss today how we characterize test methods and what we mean when we're talking about characterizing test methods and why it's important. So to start with, every measurement, every test method that we do, it has error associated with the result. There is variability in what we do. It is important to understand this variability and this error. As Steve pointed out, what you're looking at, where you are at your project will determine what accuracy you require. Also, when you're looking at the accuracy of your test methods, you want to know what effect that will have on your models or on your equations and what you're getting out at the end. If you're getting plus or minus 10% in the number you get from the lab, how does that affect your power calculations or your models that you're going to then be working with? So it's very important to understand test methods and their variability and the associated errors with them. So where does this variability in test methods come from? Every test method will have an inherent, just random variability. You can never do the same thing exactly the same. Also, samples. Samples are variable. You never get exactly the same sample. Expanding that, looking a bit further, when you have different people doing the test, that is more variability. If they're doing it on different equipment or using slightly different methods, again, you're increasing the amount of variability you've got. To work through these and to sort of help understand these concepts, I'm going to discuss an example as I go through. So about as simple as we can get. You have a sample, you send that sample to 3 different labs and go, how much does this sample weigh? You have your 3 labs and they come back with those 3 answers. How do you know which one's correct? How can you compare them? Which one are you going to trust? Through our characterization of our test methods and our understanding of errors, we can compare and we can decide which ones we want to use. So the concepts that I'll be discussing, and Steve has touched on all of these already, is accuracy and precision, repeatability and reproducibility, and I also finished off by talking about calibrations and the use of reference samples in calibrations. Following on from this, I'll then look in particular at our test methods, the JK drop weight test, the SMC tests, and we've also done work on the bomb ball test. And we'll look at those test methods in light of these concepts. So to define accuracy, this is the definition according to the ASTM. It's what we all think accuracy it is. It is how close are we to the true answer. The closeness of agreement between the test result and the accepted reference value. Closely associated with that is precision. I believe a lot of people regard precision basically as how many decimal places do I have in my measurement. That is part of precision, but it's not the whole picture. Technically, precision is looking at if you do a number of measurements on a sample, how close together are those measurements? That's when you're really looking at the variability in your measurement or your test method. There are a number of ways to characterize this. Standard deviation is obviously the obvious one. A good graphical representation of this, which is often used, is a dartboard. Say you're taking 3 shots at a dartboard. You're taking 3 measurements of a sample. First time round, your measurements are very spread out and they're not near the bullseye. That is low precision and low accuracy. You're not near where you want to be and you're not getting good agreement between your measurements. Improving on that, you may get your 3 measurements very close together. So you're improving your precision. Your measurements are getting closer together, but you're still not accurate. Conversely, you may have a bit more spread in your results, but you're getting closer to the true value. So that's more accurate, but slightly lower precision. And of course, what we want is high accuracy and high precision. We want our 3 measurements all to be very close to that true answer. A slightly more mathematical representation is you have your body of measurements. It's however many you take, 6, 3, a dozen. So you have a population and that's your measurements. Your accuracy is how close you are to the true value, and your precision is the spread of those results. Obviously, we would hope our results are much closer to the true value than that example. So discussing this spread of results, we're discussing variability. What we can do to examine that and to break it down is we often talk about repeatability and reproducibility. Again, ASTM definitions, repeatability is done on using the same method, on the same test item, in the same lab, using the same operator, using the same equipment, doing it relatively close together. That's getting about as good as you can get. That's you're removing as much variability as you can. That's getting down to that inherent variability in the test method. And yeah, you're removing any other causes. Reproducibility is the same sample, using the same method, but using different laboratories and different operators using different equipment. This is what you guys are going to see in practice. If you send your sample to lab A or lab B, you'll see that variability coming into your test results. Little picture just to illustrate this. Repeatability. You have one person repeating the sample, repeating the sample, repeating the sample. Reproducibility is you have person A reproducing person B's results, reproducing person C's results. So really, to understand a variability in test method, when there is a number of labs and a number of users, this is your overall variability that we're looking at. Moving on, and I mentioned calibrations. As Steve said, we used to use the term calibration with respect to analyzing the SMC results, but it's not quite technically correct. The important thing to know about a calibration is an operation that corresponds, it establishes a relationship between the measurement result and an indication. Essentially, calibration is a process of getting your instrument response and relating that to a known property. In the example that I mentioned earlier, we're looking at electronic balances. The instrument response from the electronic balance these days is a voltage. You put your sample on the scale and the little piezoelectric crystals get squeezed and produce a voltage. What you'll have is you'll have a technician come in with a standard 1 kilo mass. He'll put that on the scale and go, that voltage equals 1 kilo. And with these reference samples, what this means is that technician's reference sample will be related to another one, which is related all the way back to the reference sample for a kilo, which is a platinum cylinder sitting in Paris. This means no matter where you go, you know that a 1 kilo at lab A is going to be a 1 kilo at lab B, because they can all get traced back to that initial total reference sample that is 1 kilogram. So a calibration is you know what your answer should be, you look at the response that you get, and you bring them together. So essentially you're getting an instrument measurement, a voltage, or a displacement, or whatever it is. You know what the reference value is, and you line them up. Okay. Yeah. And again, I'm going to come back to variation and the spread of results. I mentioned before that often you will define it as a standard deviation. Another very common way to do it is what we refer to as the 95% confidence interval. It's easy. It's the range that will cover 95% of your responses. And it is a very practical way of characterizing what that variation is, what your error is. So if you know your 95% confidence interval, if you get an answer, you can be 95% sure you are that far out from the actual answer that is true. Bringing this back to our example, let's actually look at the error bars on these three labs. Lab A, not too precise, their error bars were plus or minus 0.1. Lab B, using maybe a slightly different method, much more precise, so right down getting to a gram level. Lab C, somewhere in between. Now, if the actual mass for that is 5.005, what does that mean? That means that both Lab A and Lab B are correct. Lab C have done something wrong. Whether they screwed up their calibration, whether they hadn't retailed the balance, whether there was something underneath the pan, these things can happen. So we have two correct answers, one more precise than the other, but they're both correct. The only way you're going to really know if Lab A or Lab B or Lab C is correct is by looking at these and comparing. If you just get the one answer with nothing to compare it to, you just essentially have to take it on trust. Now, what does this mean for comminution test work? With comminution tests, whether it's the AK drop weight, whether it's the SPI, whether it's the bond, there is no reference sample, and we cannot calibrate. You cannot take your bond bore mill test and adjust it so you get the answer that you want. So how can we know how accurate these are? The way we do these is through the comparative testing methods. As our SGS colleagues here know, the comparative testing program is you get the same sample, you send it to all your labs and get everyone to test the same sample. Hopefully everyone gets the same answer. But yeah, these are often used as a quality control measure. That is the primary use of them. It will identify any lab that is out from everyone else. It will identify a lab that has issues. Also, it's a great way of characterizing a test method. You really build up a very robust population of results that you can look at, and you can really nail down your variability in your test method and how accurate it is. So JKTech runs comparative test programs. As Steve mentioned, we've been running them for over a decade now. We've run quite a few. The results I'm going to discuss later are from our 2015-2016 comparative testing program. I'm currently finalizing our latest one, our 2018-2019 program, and I'll be presenting some of those results of Postmin later this month. Unsurprisingly, these are quite close together, so yeah, it doesn't really matter which one we talk about here. They both are a great example of what we're looking at. So removing variability. JKTech will prepare all the samples for all the labs. We're trying to remove as much variability as we can to get down to the actual variability in the test method. So JKTech, we go through, we prepare all these samples from a material that is chosen because it is quite uniform and quite good to work with. And then we also provide every lab with duplicate samples. In my previous life, in previous comparative testing programs I've been involved in, it was just a single sample. There are reasons to do that. It keeps it nice and simple, and we did those quite often. But the use of duplicate samples allows additional analysis. It allows us to start looking at repeatability versus reproducibility. It gives us more data to work with, obviously. So here's what we got for our JK drop weight results. So along the bottom, each bar is a single tester. Some labs have more than one tester, so they got a couple of sets of duplicate results. So what we would hope for is nice little short bars like that, where a lab gets their two answers very close together. We get other labs where their two answers are the top, the actual values are the top and the bottom of all those bars. So very big bars means a lot of difference between those duplicate results. Obviously, looking at this, you can just see by eye, something went wrong with those two testers. We then did, during our stat analysis, using the Grubbs test, we did classify those or show that those are statistical outliers, and we removed them from the rest of the analysis. We also went in and we dug into those results and determined what the issues were. And then we actually, to be honest, we lucked out with those lab. That lab shut down about a month after the comparative testing program. So it saved us a bit of work for patching it up. But if we get results like that, we will work through the lab. We will try and determine what the issue was. Any lab that gets results like that, we'll work on it. We will send them follow-up samples and we will bring them back in line with everyone else. So for the analysis of these results, easy, we just get our average mean value, which in this case, because we're looking at the SCSE, we got 10.81. Associated standard deviation, which then is used to calculate your 95% confidence interval, which is your effective error in the test method. So for this, we did quite well. I'm quite happy to say plus or minus 5% on the SCSE value. I'm also quite happy because the SCSE also relates back to the SG. So we're not also looking at the variability in the breakage, we're looking at some of the variability from the SG measurements, and even combined, we're getting this down to plus or minus 5%. With the duplicate samples, as I said, we can start looking at the repeatability variation through what's called the ANOVA analysis, and specifically the within lab mean squared from the ANOVA analysis, which can be used to calculate effectively the standard deviation of those repeat samples, of the duplicate samples. So from that, the repeatability standard deviation is 0.18, and comparing that to the overall standard deviation, we see 2/3 of the overall variation is inherent in the test method. The repeatability, like if you bring the variation down as much as you can, that's 2/3 of the variability that we saw overall. What that means is we have really good agreement between our labs. This is a robust test. There's great agreement between Lab A and Lab B and Lab C. Similarly, SMC results. Again, that one lab, they did better with the SMCs. They didn't make the same mistake they did with that. So we actually had no statistical outliers in that one. Again, quite happy to say, our mean value, it's at the third decimal place, it changes. But yeah, we're very happy to see such very good agreement between the JK drop weight and the SMC test. Standard deviation for the SMC test, and hence the confidence interval, is a little bit higher. We're just under plus or minus 10% from the SMC test in this program. Going into the ANOVA analysis and looking at the repeatability, we can see just over half of the overall variability that we saw is inherent in the test method. So again, we're getting quite good agreement between the labs with this method. Following on from that, with this program, we also did the bomb ball mill tests. We don't always look at this because obviously as the licensing body for the JK drop weight and the SMC, that's what we're interested in. But we thought that would be useful to have a look at the bond, and it did prove a very interesting exercise, and we're getting quite a bit of mileage out of these results, and the industry has been finding it quite interesting. Again, we do have outlier, again, determined to be an outlier via the Grubbs tests. And I believe, if I remember correctly, that one actually just came down to a data input entry. It came in the calculation method for the P80. They'd made a little typo in their spreadsheet in the P80 calculation. I did discuss that with them, and once that was corrected, it did get pulled back down there, but we left the results as is, their analysis, and actually took that one, because there was a known issue, we took that one out for the further analysis for the average and the confidence interval. So we had a mean value, average value of 15.4, standard deviation there, and that works out to a 95% confidence interval of plus or minus 14%. So not as good as the SMC and the drop weight test, but again, you need to know what you're doing with the results. If you understand what your error is, you can work with it. The interesting thing, especially with the bond test, is looking at repeatability. The repeatability standard deviation is only a third of the overall variability. So that means almost 2/3 of the variability that we saw in the Bomball results came from differences between the labs. So there's definitely, I think, work that could be done to try and standardize that test and get better agreement between the labs. Cool. And that's it. Thank you everyone for paying attention.